Okay, hello everyone. Uh, Before we start the course, maybe let me tell you about the schedule for the midterm. I think it's better to have the midterm on the last week of April, right? Last week, because uh, if you have the midterm on 19th to 23rd, I think you have another midterm, right? Yeah, I think in the last week of April, I think it will be better. And I think it will be better if it's Monday, right? Monday 26th, right? In the early morning. Or you have other preference? Wednesday. That's also good. Good. It depends on you because you will have at least some TA session on Friday, right? And maybe you are still on fire, so Monday. But it's up to you. Okay, well, I think we can discuss about the day. Okay, but at least last week of April. Okay. Now, for today's course, I would like to maybe explain a little bit about uh, some formula for these uh, four functions. Okay, so basically, after we are discussing the Taylor and Maclaurin and um, how to determine whether they are can be expanded through a power series or not. Actually, you can expand the functions if the functions follow the some rules about the error. Okay, so if you can limit the error until 0, then you can use all this function or expand this function into a power series. And in your textbook, actually, we only have 1, 2, 3, 4, 5, 6, and maybe 7 with the binomial. But I think I will not uh, include binomial in my courses for now, okay, because I think I don't really have time to explain that. So these 6 functions is the basic functions for Taylor or Maclaurin expansion. Okay, so your question or your problem in the textbook is maybe composed of this function. So maybe it's multiplied by x or multiplied by x squared. Okay, but the basic formula is from 1, 2, 3, 4, 6 functions. Okay, so from the um, 1 over 1 minus x, that's the very basic power series, right? And e to the x, and later we will discuss this formula. I think I will discuss sine and cos. Okay, and tangent and ln, it's actually quite easy to approach because you know that tangent inverse, you know the relations between. Let me give you the clues so that you can expand by yourself. So tangent inverse can have relations with 1 plus x squared, right? Through the integration, right? And ln, you can also have relations with this, right? With derivative, okay? And if you have this kind of formula, these two formula here, then you can relate to the formula number 1, right? So you can try to expand this first with the similar approach with this formula. and then you can integrate or differentiate. Okay, it depends on tangent inverse or ln. Okay. Okay. Now I will go to sine and cos to see how we can use that, um, at least the formula for Taylor and Maclaurin. So let me start from sine. Okay, so let's just find the Maclaurin series for sine x. So we can start by writing all the possibility for sine x to be derived. Okay. So first, the original function is sine x, and for Maclaurin, we are inputting 0 to our function, and we evaluate, and then the same thing we differentiate, and it becomes cos. And actually, if you see the graphs from all the 6 formula, the 6 functions that I mentioned before, you will see some kind of pattern that I think we have discussed before, that the graphs of the derivative will, or the the derivative will be approaching the original function if you increase the degree of n. Okay. And I will stop until fourth time differentiations, because it's going back to the original functions, right? Okay. Now we can set up our uh, expansions. They start from f0 and then f prime 0, divided by 1 factorial plus, oh wait, dx. So this is our expansion for the Maclaurin, and we can evaluate. So fx, evaluate all. So x minus x cubed 3 factorial plus x5 5 factorial, and we can uh, set up our sum. We can start with positive. Let me write the negative 1 with power of n, and then the formula is using odd number, right? So we can set up odd number formula inside the sum. You can actually also using um, proof to make sure to confirm that this expansion is true. Okay, or you can use the inequality to prove that with the Rn, and also you can use the graph to approach the original function sign. Okay. Now we can say that the sign is represented by the series. This series. Let me. Okay. So Maclaurin series, you try um, to derive several times. Okay, for the function. Uh, put 0 if it is Maclaurin, and then expand the series, and then find the formula for the series. Mostly, that's what you are going to do in the Taylor expand or Maclaurin series. Okay. Okay. Any questions? Any questions? I hope you can familiarize with the sum formula. Basically, this is the odd number, right? Because we are having 1, 3, 5, 7, and then alternate sign, right? Positive, negative, positive, negative. So positive, negative, we have the alternate sign here, okay? And for the 1, 3, 5, 7, it will be the odd number, okay? And my suggestion, every time you are having your sum here, try to check with n 0, 1, 2, at least 3 terms to check whether the sum is correct. Okay. Now the next functions, so find Maclaurin series for cosine x. Now we try for cosine x. Can you try by yourself? Let me give you maybe 2-3 minutes to try. You can start to write the cos and then the next derivative. Maybe try it several times, 4, 5. Write the expansions and write the sum for the formula. Okay. Good idea. Good. Okay. Anyone find what the sum is? And for McLaren, don't forget to input 0 to the x. Okay, so most of you, I think, understand how to use the series. So you can start by using this and try to find derivative, okay, maybe 4 or 5 times. Try to input the 0, it will be 1, right? So the first term will be 1, but we can look this cosine as so cosine x is actually a derivative of sine, right? We can actually find the expansion for cosine from sine x. Okay. Now, sine x, we already discussed previously. So it will be x and then x cubed and then x5. Let me write maybe until 7. Okay, and we need to derive this to become cosine. So cosine x will be derivative of x is 1 and then 3x squared, 3 factorial plus 5x4, 5 factorial. And we have this kind of pattern. We can simplify this. And we get this result for cosine. Okay, so it will be now the even number, right? Now we can also write the sum. The alternate sign. and the even number as the formula for n. Okay, notice that sine and cosine at this point, we are using it for the Maclaurin series, which means the x is 0. So if you want to maybe evaluate the Taylor series at some a, you can just change the 0 to some other value. Like for example, pi over 3, pi over 6 in trigonometry cases. Okay. And maybe the formula becomes a little bit long because of the value. This one? This? Is it true? Is it correct or not? Mm-hmm. But but 0. Start from 0. Okay. Remember, Taylor and Maclaurin usually it's the default is start with 0, because we know that 0 factorial is 1, right? So it's correct for the value for 0 factorial also, right? Another important things for Taylor or Maclaurin is they can help us to approximate, at least for some integration that we couldn't handle. Like for example, the e to the uh, negative x squared dx. Yeah, this is the non-elementary, right? Non-elementary functions, and we theoretically we couldn't able, or we cannot integrate this at all, right? But with series, we can approximate. So first is, remember we have the e to the x. This is x with power of n, and divide by n factorial. Now what we can do is we replace that x with negative x squared, okay? And write the sum. And this is our sum for e to the negative x squared we can simplify the sum, become -1, as separation the alternate, and x to n, and we can expand this series, become 1. Yeah, that's 0, and then 1 will be negative x squared, 1 factorial, and plus, and then minus, and this is our expansion for e to the negative x squared. And then to find the integration, we can integrate all of this, right? And put the x at the end. So integral of negative x squared dx, we are using the powers, the Taylor series or Maclaurin series. It will be the constant plus x minus x cubed, and then 3, 1 factorial, plus x5, 5, 2 factorial, and then minus x6, 3 factorial, plus until some point. And we can have this as let's write the series in n, maybe here. Okay. Oh, wait. I think this should be 6, sorry. And this should be 7. Okay, that's even and odd, yeah. And the series, this will be converges because the original series, the e to the minus x squared, also converge. And you can find also the error if you want from 0 to 1. Okay, so let me review a little bit for this Maclaurin or Taylor. Any question first? Any question? This is just example that you can use it for some functions that are non-elementary. Okay, non-elementary. Uh, let me review a little bit of so we can use Taylor series. Take the new function or Taylor series from the old series. For example, if you have functions of x cos x, okay, which means you have the cos x, right? You have the sum, blah, 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 right? The even number. Right? And you have x. What you can do is you can input the x into the equations, so you get the +1 here. Okay. So whenever you find any functions that have relations with the basic functions in Taylor and Maclaurin, the 6 functions that I gave you before, the sine, cosine, 1 over 1 minus x, e to the x, and then the tangent inverse, and ln 1 plus x, all of that, you can have a composed function. So like x cos x, or maybe tangent inverse, and then inside the x, it's replaced with x squared plus 1 or x plus something. What you can do is you can replace that and use the basic functions and try to find the relations. Okay, that's the first what you can do for the Taylor and Maclaurin. And also you can do the reverse. Okay, so for example, if you have the series power series, if you know the power series, if you know this power series, what this could be, now you can also try to relate with our uh, the 6 functions. Okay, if you see the x with the power of n and n factorial, you will notice that probably will be related to e to the x, right? Because e to the x is like this formula, the sum. Now you can write down the formula, arrange another formula from the original one. We can maybe include the -1 with 2 and x, so we can have -2x with power of n and divide by n factorial, which means this is the same or similar formula with the e to the x. The difference is the x, right? We replace the x, so it's replacing x with -2x. So we can conclude that the function that's represented by functions is, or functions that represented by the series is e to the -2x. So we can also figure out from the series and then try to find the functions, or uh, we can see from the functions itself if it is composed with our 6 functions. Then you can also try to find the formula. And if it is maybe composed with all these 6 functions, maybe, for example, if fx is e to the x and then sine x, what you can do is you have the series, right, for e to the x, and you have series for sine x, right? What you can do is you can multiply, okay? You can multiply. So you can multiply. And of course, since it's a polynomial, so you need to be careful for multiplication because it's a long multiplications. And you will get the results after you multiply. Okay. Also, you can also, if you have functions is equal tangent x. Tangent x is sine x divided by cosine x, right? So this approach is basically you have expansion for sine and you have expansion for cosine. And basically we are having the long division procedure. So you need to try one by one and then having all this. Okay. So for example, the factorial need to be calculated to help you evaluate this division. So x 3 factorial, right? 6. Maybe only maybe 3 or 4 terms. Maybe 3 terms is just enough, and this also maybe 3 or 2 terms enough. This is 1. So you can divide this and find the tangent x. So maybe to help you see the pattern, let's start from x, and it's become x, and it's become x cubed, and it's become plus x5, okay? And calculate this minus, you get the result here until you find so the tangent x will be the x, and because it will not stop, okay? You can just maybe after a few terms and you can just stop and then put into the formula here because it's basically it's you will not see the end, right? So 1/6 minus plus half, so half minus 1/6 is 1/3, right? So this is plus 1/3, and then maybe from here 1/24 and 120. You minus this, and you get 2/15, right? But because it is a polynomial, it won't stop, and you will not have 0 here. So you just write down the the first few terms from the equations. Okay. And don't forget that the same thing when we multiply e to the x and sine x, we multiply all actually, but maybe you can just focus on the first few terms, and that's okay. And that's it, the chapter 11. There's still one section in chapter 11, but I think that is more likely to be, it's the same thing as we discussed before, the remainder, the error, but it's more in applications using approximations and other um, applications like in physics, in astronomy. But I think I will skip that section because we already have the concept. Okay. So what we will do next is we will go to the chapter 12, the factors. So for chapter 11, I will send you the notes, the lecture, and we will have the review maybe before the midterm. Okay. So we will go to the chapter 12 first and then go for review for chapter 11. Maybe 1 day review or maybe a 1 hour review. Try to solve some problems from your exercises. And then after that, the midterm. Okay, so last week of April. Okay, last week. So if not 26, 28, Monday or Wednesday. I will tell you later. So you will have TA session on Friday before midterm from your TA. Or maybe before that, we can have review also. Okay. So now, because we have a limited time, I will go to the next chapters, the factors. Let me just write in the new page for the factors. So chapter 12, vectors. And because I know some of the uh, physics, you already also learned the factor, but I think I need to review also. But maybe a quick review. So what is factors? What is factors? So usually if you have like, or you want to illustrate maybe force, right? In the physics, you have maybe directions and you have value, right? Maybe 5 Newton. And you can also have the force with the different directions. The vectors can be defined as it's having a scalar value and the directions, and it's having own directions. Okay. But before we go to the vectors, let me go to the coordinate system. Okay, so 3-dimension coordinate system. Just a review for the whole things. Okay, so first we'll start by um, telling you the default or the coordinate system in 3 dimensions. So we'll start by saying this is x, this is y, this is z. And how we determine that? If you are If you remember, we can use our right hand to define the z directions. So this is will be the y, and this is will be x, and this will be z, right? Okay. So if you remember that, then we are actually using the same concept. Okay. The next thing is if you have, or let me write in so x, y, z. So if this is the zero or origins. Okay, they always start from zero for 3D. Uh, let's using let's use the coordinate system as we are passing through some points, like we are walking through this all three coordinate system. So we are walking through x here, maybe a, or maybe number you can put 2, 3, anything, and then moving to this, maybe b, or maybe I'll take a long b, maybe until there, and then take some point here, um, maybe c. If I define a point P here, we can write this P, the coordinate P is A, B, C. Okay. This is just to refresh our mind how the coordinate system works and how the positive, negative in 3 dimension for coordinate system. So if you are going backwards here, it will be negative. Okay, so you're going here is also negative. Going here is also negative. For example, you start from 0 and going here, it's positive, but you are going here, maybe negative b, so negative b. But going up, it's still positive c. Okay, just a quick reminder. So another thing that important is the surfaces. Okay, now in 2 dimension, if you have graph x, y, all right, you will have um, curve in this is terms for 2 dimensions. Okay, so if you have 3 dimension involving x, y, z, you will have a surface. Okay, not a curve. You will have a surface in 3 dimension. Okay, so if you have the Cartesian x, y, you can also always having the curve, right? But if you have 3 dimensions, you will have, we call it the surface. Okay. What the surface is, let me start with the first one is maybe z equal 4 and maybe y equal 3. Okay, now if z and y is in 3 coordinate system, 3 dimension coordinate system, uh, Okay, let me write here. Okay, now z is equal 4. So 1, 2, 3, 4. What surface really means is if you're only having z equal 4 as your equations, that means is you are having this entire surface. So it's like in the z equal 4, you have unlimited surfaces for x and y. So 2-dimension x and y, unlimited uh, amount for x and y. But it is slicing the 4. Okay, slicing this 4, z equal 4. That's for z equal 4. Same thing with y equal 3. So you have 1, 2, maybe 3 here. It's like a slicing from here. So you will have infinite amount of 2-dimension x and y at y equal 3. Okay. So I hope you get the idea for the surface. Okay. Now that's a single point, right? Single point in the 3 dimensions. Now if you have, um, let's say a circle, x squared plus y squared equal 1, and z equal 3. Okay. Now you will see it's having z. Let me write 1, 2, 3, 3 here, z equal 3. But in the x and y, now you have a restriction, which is x squared plus y squared equal 1. So you have a circle with radius 1 on z equal 3. So you have a circle here. Okay, get the idea? Okay, so you will have a circle here. So it's x squared plus y squared equal 1. So it's like you can, if you see from above, and you are imagine the Cartesian, you will see the x squared plus y squared equal 1, right? But then you can see from the other side, it's actually on the level on 3 in z. Okay, so you need to be able to see from other angles if you want to imagine in the 2 dimensions. Okay. This 3D system or a coordinate system is very I think this is very important if you are going to see a lot of graphs, especially 2 dimension to 3 dimension. And you need to be able to visualize if you have 3 dimensions, like a structures, like a building, like equipment that you need to project into 2 dimensions. You need to be able to translate the 3D to 2D projections. There's a lot of software for doing that, but you need to know how it works, how the concept works in 3D system. Now, if you have, okay, so this is the first case. a circle and then z. Now the second case, if you are having only this, but can you imagine how the 3 dimensions looks like? If you have restriction like z equal 3, then you are having just this a surface, right? So if you are having uh, this x squared plus y squared without any z involvement, but you need to draw the 3 dimensions. So you can do that. So let's start by uh, making this circle is x squared plus y squared equal 1. But then because we have not yet determined how we restrict the z, so the z will be unlimited. Okay, so it will be going from here to here to here. It's actually going uh, infinitely above and the bottom. Okay. Now we have now the cylinder, right? The cylindrical. Now we have the cylinder. And the next thing is, if this is infinite amount, then we actually can limit maybe from z equal -2 until z equal 2. Then it will be limited to that level. So we have the solids, right? Okay. Maybe if we can limit the cylinder maybe from here until here, or maybe just a positive one. So maybe I'll write this as x squared plus y squared. We can write with the inequality like this, and z maybe 2, z 4. And this is our solids. So we will have the surface and we will have the solids. Okay, so this is for the solids. Okay, let me check your understanding. If you have if equations is or equation is y equal x, describe and sketch the surface. So if we have y equal x, how you can describe the surface? So first is the if you so you can start if it is you can describe in 2 dimensions. You can think in the 2 dimensions what kind of equations in the graphs. Y equal x just a line, right? And then we convert it to 3 dimensions. For example, Now this is quite tricky. If you are always having this as a default for 3D, so this XYZ, the XY is maybe here, right? But maybe if you are drawing too closely, you will not see what is the difference, right? So maybe you can rotate. Okay, you can rotate just to see the angle from other side. So maybe you can have Z here, and then maybe Y is there, and maybe X is here. So if you have a graphing website or any software that you can rotate the axis, and you will have maybe like that. And at the Z level is actually going infinite amount, right? So this is the surface. So this is y equal x, and z is actually 0, right? Because we are not defining this z. So whenever we are define any axis as 0, which means at that very directions, it will be unlimited. Okay? Like from before, we are determine z equal 3, so x is 0 and y is 0. So both of two axes will be unlimited. Okay. Now, the other thing in this introduction of vectors, um, if you have 2 points, for example, P1 and P2. Let's say P1 and P2 is described as x1, y1, and z1, and P2 is x2, y2, and z2. If you want to evaluate the distance between these two, we can use the distance formula. Okay. So distance, this is distance. And we can use the, if you want to use the Pythagorean approach, we will get x2 minus x1 squared, right? And then y2 minus y1 squared. And then plus c2 minus c1 squared. Okay. This is just reminder for the vectors. Okay, from this formula of distance, we can have formula for the spheres. Okay, let's say that's our sphere. If our sphere here is this is the center of the sphere, let's say the C, and the surface, one point on its surface is P. Let's say that P is x, y, z in coordinate x, y, z, and C is in the coordinate of h, k, and l. Now we can have this relation that PC is our radius, right? And we have relations from distance formula. So this is our radius. And if we are looking at this formula and squaring both sides, let me rewrite the x minus h on the left. And we will have the sphere equations. If the center is origin or 0, 0, 0, then we have x squared plus y squared plus z squared. This become our sphere equations. Okay, let's see example. So if you have one, you have inequality, 1 less than equal the sphere, x squared plus y squared plus z squared, and less equal 4. So let's sketches the region. So it's from 1, and then the sphere, and then 4. Can you think and maybe sketch how it looks like? And all of these introductions, the three-dimension coordinate system, it will help you, especially for the surfaces on the last section of chapter 12, the 12.6. That will be a lot of um, sketches and how to describe the region. So for this case, the sphere, uh, if you are having the equation of sphere, it's x squared plus y squared plus z squared, right? It's equal r squared. So this part, this 1 and 4, is r squared, right? So if you would like to have the r, then we can see 1 and 2, right? And if you are sketching the curve or the surface or the solids, since its origin is 0 or at the very beginning, so let me make a circle here to represent a sphere, and maybe circle like that. Okay. Now the radius is from 1 to 2. Let's just see from because radius, if you are seeing the radius from this to here to here to here, all will be the same radius, right? So let's say we are looking at here, this line. Let's say this is 1, this is 2. So this will be 1 to 2. So let me cut this 1, and this is 2. So basically, you will have this solid. It's not really good because it's actually, if you see from outside, it's like a solid, but it's having a hollow. Okay, let's just cut this open, and you will see the inside is like this. This is 1, this is 2, and this is the solids. Okay, can you imagine that? So you are like having a ball. The ball inside is hollow. Okay, so if you are looking from outside, it's actually is like a solid, but actually it's hollow inside. The hollow is from 1 to 2. The solid is from 1 to 2. So from 0 to 1, all of this is empty. Okay, so it's like a ball, but it has a hollow part inside. Okay, that's all the intro for the factors, the 12.1, the 3D system coordinate. Okay, we will going back to see all this, the cylinder, the sphere in the 12.6 later, and maybe some parts in the integrations in the last chapters. But for now, let's move on to another section in factors. I think it's just an intro. So Let's checking the vectors. So the vectors 12.2. So the vectors, it depends on you how you describe the vectors with. For example, if you have A, B, you want to describe this as V, that's fine. If you have C, D, let's say U, but with the arrow at the top, that's also fine. That's usually the common written expression of vectors. And we always having the starting point, the start point, or initial point, and the terminal point. And imagine if this is equal length for this U and V. We can also say that U and V is equal or equivalent because it's having a different starting point and initial point, but the length is the same. And if we are having the directions, like let's say we have the A and then to B, and then we are moving one more time to C. Um, this is the arrow, the directions. From A to B to C, we can say that the total length or total displacement from ABC we can write down in terms of vector. So vector AC is vector AB plus BC. So I always suggest you to, if you want to visualize the vectors, my preference is to visualize the vectors as the distance we travel with certain directions. That's the, I think, my preference. Okay, so if you are traveling from A, B, C, so to sum A, B, C, you can sum up as a length from A to C. Okay, that's just refreshment, the idea how to define. And if you have, or if you remember, we have the vector addition. So these chapters I will going past the early introduction for the vector because you already have the concept. So I just refresh your mind. But maybe in some parts I will slow my my lecture. So if you have, this is U, this is V, this is U plus V, this arrow like that. And you can think this UV as in terms of, okay, another V and another U. Okay. This is we call parallelogram. So it will help you to establish, for example, you have this A and then you have this B, which means this is the same B here, and you can make A plus B here. Okay, I don't think we need to write down the official theorem for factorizations. It's already well known, and you can apply it for some exercise or problem. Okay. Now we also have scalar multiplications in a factor. So if C is scalar and V is factor, then CV is a factor whose length is C times, okay, the length of the factor V. And with same directions as factor V. If C is positive and opposite directions, if C is negative. If C is 0, then V is also 0. So CV is 0. I think this is also understandable, not really that difficult. Okay, that's the scalar multiplication. So if you have, for example, let's say phi, and the other one is this 2phi, okay, and the other one is this half of phi, and if you have opposite directions like this one, then it will be negative phi. It's too long here. So if you have u minus v, for example, this is actually u plus minus v, okay, in terms of factor addition. So if you are, let's say, drawing the vectors like this. Let's say this is U, this is V. We know from previous, this is U plus V, right? But if you want to write U minus V, you can write the directions as this, the negative, so the opposite one, and then this will be your directions. So this is U minus V. Okay. And now, after we define the length, the geometric space for the vectors, we can also define the components of a vector, which is related to the coordinate system. Okay. In 2 dimensions, let's say we have the vector A, we have A1, A2, XY, this is XY. Okay. And in 3D, we have 3 X, Y, Z. And let's say we draw the 2 dimensions, and let's say the A is this vector. Let's say this is A. So that's the vector. So we have A1 at this point and A2. Let me write in more. So A1, A2, the coordinate. And A itself is, notice I write different brackets here and here. If you see the brackets like this one, this means the vectors, okay? Which means A1 position minus 0, okay? A2 minus 0, okay? Just a reminder for you. And of course, we also have the 3 dimension. So this 0, and if we have here the position A1, A2, and A3, if this is our vectors, A, so we can define A in 3 dimension, A1, A2, A3. Okay. So if we are having different start point, let's say from here, then our vectors will be depends on from where we start. Okay. Let's say let me just write the theorem and the definition. So given A is and B is, So A is representing, so factor A is representing AB. Okay, so A will be okay. So it depends on your starting point and then your terminal point. You can define your factors. Okay, just uh, summary and review for factors. How many we have? Um, I think I will continue the later part on Wednesday and move to the next section on factors. I will go emphasizing maybe on the uh, the dot product, cross product, and the equations for plane in the factors. Okay. So I will stop here and I will continue next Wednesday. And I will put the notes for chapter 11 later after I put the video recording. So you can have some study for chapter 11.